All right, so here we go. Another example. We've got the limit as x goes to 0 of x e to the x all over the quantity 1 minus e to the x, right? So if we take this limit, we're going to get 0, right, times e to the 0, which is just going to be 0, and then it's going to be 1 minus e to the 0, which is 1. So you end up with 0 over 1 minus 1, which is 0 over 0, right? There's that indeterminate form, right? So this means that we can apply L'Hopital's rule. So that's what we're going to do. We're going to apply L'Hopital's. And we're going to take the derivative of both of these. So we're going to take, this is going to be equal to the limit as x approaches 0 of the derivative with respect to x of x e to the x all over the derivative with respect to x of 1 minus e to the x. So in the numerator, we're going to have to use the product rule, right? So we've got x times e to the x, so it's the first function, x, times the derivative of the second function, which is e to the x, okay, plus the second function, e to the x, times the derivative of the first function, x, and the derivative of x is just 1. So there's the derivative of x e to the x. The denominator, we've got 1 minus e to the x. The derivative of 1 is 0. Derivative of minus e to the x is minus e to the x. All right, so let's see if we can find our limit now. And you're not always going to be able to find your limit right away. Sometimes you might have to apply L'Hopital's 2 or 3 times before you can get to your limit. But I think in this case it's going to work out. Let's see what happens. So we get the limit as x approaches 0 of x e to the x. That's going to be 0 times e to the 0, so 0 times 1. So we get 0, I'll write it out, times e to the 0, right, plus e to the 0 all over minus e to the 0. Well, the first time is 0. It's 1 over minus 1, so our limit is negative 1. You might want to graph that function. Just take a look and verify it graphically that our limit for that function, right, as x approaches 0 is going to be negative 1. Even though it's undefined at that point, it's indeterminate at that point, the limit is going to be negative 1. All right, I'm going to do just a couple more examples. But these examples that I'm going to do are basically for some of the other indeterminate forms. We haven't really talked about these, but we've got the limit as x approaches 0 from the right of tangent x times the natural log of x. If you take this limit, right, tangent of 0 is 0. And then we already talked about the limit as x approaches 0 from the right for the natural log of x. That's going to be infinity. So this is this indeterminate form. Right. So it's an indeterminate form, and we can use L'Hopital's here for this, but we need to change this so it's either 0 over 0 or infinity over infinity. So is there a way that we can maybe rewrite this so that we've got 0 over 0 or infinity over infinity? And there's a pretty easy way to do this for this one. We've got a trig function, right? I'm going to write this tangent of x as 1 over cotangent. And that means you're going to think you can rewrite this as the natural log of x over cotangent of x. So this is in the form infinity over infinity. And now we can apply L'Hopital's. Right? So if we apply L'Hopital's now, we're going to take the limit as x approaches 0 from the right of the derivative with respect to x of the natural log of x all over the derivative with respect to x of cotangent x. So the derivative of natural log of x is pretty easy. That's 1 over x. So we get the limit as x approaches 0 from the right of 1 over x all over. And the derivative of cotangent, let's see, the derivative of tangent is secant squared. So this is going to be negative cosecant squared x. All right, so we want to know what's the limit as x approaches 0 for this. Let's see if we can maybe rearrange this. All right, I'm trying to think about how I might want to rearrange this thing. I'm going to rewrite things right now. As it if you took the limit as x approaches 0 from the right of 1 over x, it would go to positive infinity. So this could be the case where we're going to get infinity over infinity and you have to apply L'Hopital's again. But what I'm going to do is I'm going to rewrite this, I think. Let's see what happens if we rewrite this. The limit as x approaches 0 from the right. 1 over x, I'm going to leave it like that for now, but I'm going to think about this negative cosecant squared as negative 1 over sine squared x. All right, I like the way that looks. Because I'm going to rewrite this now. We've got the limit as x approaches 0 from the right. This becomes negative sine squared x over x. But we just found the limit of sine of x over x. So I'm going to rewrite this as limit as x goes to 0 from the right of sine of x times sine of x over x. And that's going to be equal to 0 times 1, which is 0. Right? So the limit as x approaches 0 from the right of tangent x natural log of x is 0.